This is the 2021 networks connections at this point. So let's talk about question 1. It says, for a connected graph with 4 vertices, 4 edges, the sum of the degrees of the vertices is what? I would suggest with this one you actually just draw out the graph. Got 4 edges, 4 vertices, 2, 2, 2, 2. Yeah, 2 is the answer. The next one here talks about the Eulerian circuit. Now, with Eulerian circuits, all the degrees of the vertices need to be even. In this case, B, if you look at that condition, it is the correct answer for this one, because we've got a total of 4, 4, and 4. 2 in this case. Keep in mind a loop counts as 2, so all the other parts here don't satisfy that even vertex condition. Now, with this particular bipartite graph, you can see with this bipartite graph, we need to assign someone to play in every position. I'm just going to jump straight to this answer here and say that, obviously, since Charlie doesn't have a specialization in small forward, we can say that that is not possible at this point. How many faces does this graph have? Now, with this particular graph, if you rearrange this graph so that you pull this point over there, okay, and you end up having a non-intersecting graph, which is what you need with the investigation like this, you'll find out that the faces are 3, because you'll end up having one face, another face, and the outside, which is another face out here. Now, question 5 talks about a particular network. Now, with this particular network, it's asking us to use Dijkstra's algorithm. Now, keep in mind, Dijkstra's algorithm, it's all about finding the shortest path. Now, something says to me here that the fact that it's asking for the critical path, I can immediately kind of discard answers A and B in this case. Critical paths relate to the networks and crashing in this case. But since we're talking about the Dijkstra's algorithm in this case, let's follow this idea that we're trying to find a path that goes from A to J. Okay, now with A to J, let's investigate all the possible paths. I guess it doesn't really necessarily need Dijkstra's algorithm, but it's really just talking about the shortest path to get to A to J. Now, if we look at the top one, AEJ, okay, AEJ will get us to the path there in a total of 47. If we look at a DE, in this case, we get a DEJ, we get 6 plus 15, which is 21, plus 23, which is 44. And in this case, since we know that one of our answers here is, in fact, the shortest path is 44, we conclude that might be the case. I'm just going to have a look at this answer here and see what this yields. So 22 plus 8 is 30. 30 plus this is equal to 42, 48. So you can see in this case, this could have been a potential distractor, but in this case, shortest path is 44. Looking at this question, it's asking us to find the minimum spanning tree, in short. And if we investigate this, these values here will definitely be part of any investigation that we're going to do. Now, our whole point of this is to make sure all nodes are connected. So the nodes that we really are in question with are these ones here. Okay, so I'm going to just start off with that in yellow. Now it says, if m equals 1 and n equals 5, we get a connection of 28. So let's investigate what each of these will give us. And unfortunately, this is the only way that we can really investigate this. So if m equals 1 and n equals 5, in this case, we still want to we still can use n as a possible path. So 5, 6, 12, 15, 19, 24, 28. So that gives us 28. So we need to go through this whole process, and in fact, if you go through one more, which is B, m equals 2 and n equals 5, I can already see that there's probably some sort of pattern, because we're going to add this all up. All these add up to 6. This is the only one that adds up to 7. So I'm presuming this one will add up to 29. So B is your answer for this one. Alright, question 7. Okay, question 7 will require a bit of drawing. Now I strongly suggest that if it gets to the point where it gets too long to complete this question, that you complete this question last before you do, after you start all the other modules. So I'm going to draw this to the best of my ability. We've got activity A, which is our starting point. So I'm going to draw here to here. Now it's A. Now B. B looks like it's got a predecessor of A and also C. So that means there'll be 2 branches that come off A. In this case, I'm going to draw B on top, and I'm going to draw C downwards. B, 7. I'm going to draw C going down here. Alright, now if you look at the next one, it's got D and E both coming from C. So D and E both coming from C. Now, at this point, I'm going to just skip ahead and see that I also have D that's coming from, B and D that branches off both an F and a G node. So, so it looks like since B and D are both predecessors, looks like there needs to be some sort of path here that joins. So D has a time of 3, and F and G branch from this section up here. So I'm going to draw this going down, F and G. I'm going to draw F going over here. F takes 4, and G takes 4. Alright, so I'm going to have a look and see now if G, so E, G, okay, now let's look at H. Activity H has E and G as predecessors, and do we have activity E somewhere? Activity E comes from C. Okay, activity A comes from C, and it looks like the reason why it's joined as well is because H comes from E and G. So H comes from E and G, that takes 2, and H in this case, F and H are predecessors of I, so F and H predecessors of I in this case here, and next one, J comes from this, J is 5, and K looks like it has predecessors of E and G, so that particular node. No, that goes to the end. Okay, so that has K, which is 7. Alright, so in this case, it's really asking us how many activities are on the critical path. And if you go through crashing in this case. Let's do it. So we get 0, 0. Oops, sorry. Okay, 0, 0. Get 9. Okay, 9. If we go this way, we get 14. Okay, 14. From this point, we get... Alright, I think the important thing as well, before doing this question as well, is working out with the direction of the activities. So, A can go that way, B can go that way. Okay, D goes that way. 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 And that way. Alright, so if we investigate the values for this now, we can see that 0 will go there, and the earliest start time for this one will be 9. The earliest start time for this one will be 9. For this one here, we'll get 14. And for this one here, we'll get... Okay, so now since we're dealing with this particular area, 9 plus 5 will give us 14 going this way. So this one here, 9, 14, 17. Okay, and this one here, if we go through the top, we get 16. But since we want to use the largest number, since we're forward scanning, this one will start at 17. Okay, and then this will also be 17, since that branches off from that particular node. Alright, if we finish off this, we get 17 plus 4. In this case, 17, so 14 plus 6 is 20. So that means this one here is 21, and this will also be 21. Okay, 21 plus 2 will give us 23 in this top branch. And 23, we end up getting 28. 28, and then we finish at 33. Okay, so now let's do a backward scan of everything. Okay, and we end up getting the following. So we get 33 goes there. 33 minus 5 is 28. 23. Okay, 33 minus 7 will give us 26. In this case, we've got 21 minus, so 23 minus 2, which is 21 goes here. From this top one, we get 19 from the top. Okay. So then if we go back this way, following this critical path, we get 21. 21 minus 4 is 17. 21 minus 6 in this case is 15. Okay, if we keep going from here, so we get 17 minus 3 is 14. And then 14 minus 5 is 9. And then 14 minus 7. Sorry, not 14 minus 7. 17 minus 7 is 10. And then we end up with 0 here. So if we see our critical path, it lies here, 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 here. So there are a total of 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 projects on the critical path. Alright, for this last question, this is quite a difficult question. The first stage for this question is to actually draw up forward scanning and also looking at what the critical path is. So just to save time, I'm going to work out what the critical path is in just a moment. Alright, so now from this point, you've got the critical path, which you can analyze, comes from A, D, G, K, L. Okay, alright, and L. Now, with this particular path, there is a total of 28 when we go through here. Now, if we look at the second part of the question, it says activity M has a duration of 2 hours. And also, more importantly, activity D is no longer required. So, in fact, this path is gone. Now it says it has an earlier start time of 17 and a later start time of 18 hours. So 17 and 18 hours. There has to be some sort of location of where this activity will go. Now, it's not just going to replace that point right there. Okay, so we're probably thinking that it's going to be somewhere around this particular region because there's a 17-hour start time and an 18-hour latest start time. So, let's have a look. Alright, so since we've got a start time of 17 hours, I'm going to just have a look at this path right here. Now 6 plus 11 means that we get a start time of 17, and since there is a slack here of 1, what I'm going to propose is that we put our M value there, and we get 17. And we need to investigate now if our critical path has changed. So we've got 6, 11, and in this case, this will be starting at 6, 11, 17, plus 2, because M now has a duration of 2. That will give us 19. And remember, we want to find the largest value in this case. So if we've got 6 and 8, okay, that's not our critical path. We've got A, 5, 7 and 8. So 5 plus 7 plus 8 is now 20. So in this case, yes, by doing this, by adding an activity M, our critical path has now changed. And let's have a look at what this duration will be. So 5, 12, 5, 12, 20, 27. And we can get this done in 27 by changing and adding this new activity. But previously, before we changed it, we had a path of 28. So A, E, I, J, L will result in 27, which means that it will be 1 hour less if we change this particular path.